So I'm going to talk about proximate quantum spin liquid state in frustrated metal. So as you can see that the term frustrated metal has been underlined because of the fact that you probably know that there are a lot of works that are going on in frustrated insulating compounds, but there are relatively less number of works that has been concentrating on finding out new interesting quantum states of matter driven by frustration in case of metals. Okay, so this particular work is going to be like the related to the work of one of my PhD students, Dishant, and of course, there are a lot of collaborators where Oliver and Veronica provided us the compound on which I am going to talk about, and Tony actually helped us a lot in performing this muon spin relaxation or rotation technique, in short MUSR, at PSI Switzerland. Okay. So let us move ahead. So definitely I am going to talk about what is quantum spin liquid and what is the idea of this proximate quantum spin liquid. So the point is that, of course, I mean, I think most of you know already about the idea of frustration and so on, but just for the sake of the students, I'll be just quickly sort of go through that. But before going there, I'm also since we are actually dealing with metallic systems, so I'll be talking about the kind of competing interactions that are present in magnetic metallic systems. Okay, so let us think about that. So now what happens is that since in metals you have a huge conduction electrons that are there, so what happens is that the local moments interact with respect to each other via the conduction electron, some kind of a super exchange interaction. And if you consider that the coupling between the conduction electron and the local moment is J, then you know that kind of interaction is known as RKKY type of interaction, and that sort of gives rise to a long range magnetically ordered ground state in case of a metal. Okay. So now, of course, if this J, the coupling between the local moment and the conduction electron is sufficiently high, then what happens is that the conduction electron sort of tries to produce a many-body singlet state with the local moments. And because of that, what happens is that that sort of screens the magnetic moment of the 4f element. Okay, and that may give rise to a Fermi liquid-like of state where there is no long-range magnetic ordering. So probably you have realized that these two sort of interactions that are competing with respect to each other, right? One promotes magnetic ordering, another tries to suppress down the moment of 4f, right? So now, of course, this kind of competition was nicely been described by Doniak phase diagram. So as you can see here, so the main point is that the RKKY scale is actually behaves quadratically with the coupling of the 4f electron with the conduction electron, whereas for the Kondo scale that sort of follows this kind of exponential behavior. As a result, what happens is that for low values of J, the RKKY scale wins over the Kondo scale and you have a long range magnetically ordered ground state. Whereas for the high values of J, the Kondo scale wins over the RKKY. As a result, you get a Fermi liquid state. So now while going from the magnetically ordered state to the Fermi liquid state, you end up in getting a point where theoretically the ordering temperature is at T equal to 0 Kelvin. And that particular point is known as quantum critical point. Of course, you would be expecting strong quantum fluctuations around that particular point. So yeah, so this is the thing that I wanted to talk about, the competing exchange interactions in the case of metals. So now let us move on discussing about the idea of frustration, which is the main ingredient in order to stabilize a quantum spin liquid state. So as probably most of you know is that if you consider this simple situation that you have a triangle, each corner of the triangle you have some Ising spin. And if you consider that the interaction between them are antiferromagnetic in nature, then you know the third spin is going to be in a frustrated state, whether it should align itself in what direction it doesn't know. Okay, and that sort of situation can give rise to a huge degeneracy of the ground state. So now the point is that the ground state or the quantum mechanical ground state of this kind of situation where you have frustration was nicely been described by this resonating valence bond model, also known as a quantum spin liquid, first proposed by Phil Anderson. And what he mentioned is that the ground state is nothing but a linear combination of all the degenerate ground states. Okay, so this is one degenerate state, this is another state. So where the thing is that if you consider H-shaped triangular lattice, and you can see that the nearest neighbors are forming some sort of singlet state, and this singlet covering throughout the lattice is different for this configuration and this configuration. Okay, so and you can sort of form this kind of huge number of different coverings of the singlet and produce degenerate states, and the ground state is a unique state, and which is the linear combination of all the states. Okay, and that from there you can sort of imagine that the ground state would be a dynamical state where there won't be any sort of spontaneous symmetry breaking even down to theoretically t equal to 0. Okay. So now the point is that since we are talking about frustration in metals, so which means that we have all the three interactions that are in hand, right? You have Kondo, RKKY, as well as frustration. So now the people started thinking about two main questions. One is that whether the presence of frustration can sort of give rise to a different sort of phase diagram that is conventionally known, as I just showed you in the last slide. Another question people tried to ask is that whether we can sort of get a quantum spin liquid state also in metals. Of course, theoretically, there are a lot of models, lot of people sort of come forward to address this issue. One of such model has been proposed that proposed some sort of global phase diagram. They actually considered some Kondo lattice model, whereas the first term is nothing but representing the RKKY type of interaction. The second term is representing the conduction electron bath, and the third term is nothing but the interaction between them represented by this Kondo interaction. And this kind of results gives rise to this kind of phase diagram, where along the x-axis you have this Kondo coupling, along the y-axis you have quantum fluctuation, which means that if you go along the y-axis, you have more and more frustrations, okay? Or reduced dimensionality can also increase quantum fluctuations as well. So the main point is that if you see this kind of interesting phase diagram, they propose different type of quantum critical points, as well as there is a possibility of having some quantum spin liquid even in the case of metals. Okay, so these are the sort of theoretical sort of background that I wanted to mention. So now the question is that, as I just mentioned in the beginning, that why there are less number of interesting frustration driven states in the case of metallic systems. So what we feel is that, in the case of insulating systems, so if you consider the further neighbor interaction between the spin moments, they decay sort of exponentially, whereas for the case of metals, since it is driven by RKKY type of interaction, it doesn't decay exponentially but follows r to the power 3, 1 over r to the power 3, right, as you know. So which means that there is a good chance that in the case of metal, you have relatively stronger further neighbor interaction compared to insulating system, which may sort of can diminish the presence of frustration in most of the metallic system, even though the magnetic moments are arranged in a nicely frustrated structure, okay? So another point is, as already mentioned, that in the high J limit, you have dominating Kondo interaction that often sort of screens the magnetic moment completely. And if it is so, then there is no chance of having any frustration because you have to have a finite magnetic moment there, right? And also, if you are thinking about probing the quantum spin liquid state in case of metals, as you know that in the Fermi liquid state, usually one would expect that the heat capacity over temperature or the susceptibility is sort of temperature independent. Right? And in the case of a sort of quantum spin liquid, in a simplistic scenario, if you have a spin on Fermi surface, that should also give rise to a similar kind of temperature dependence. So thus it is rather relatively trickier to figure it out from the bulk measurements whether you have really a quantum spin liquid or not in the case of metals. Fine. So now, so we have been thinking about these two problems that I have mentioned for the last, let's say 4 or 5 years. So what we have tried to see that we consider this particular interesting compound, cerium, palladium, aluminium, where the cerium moments are the main responsible magnetism guy, and it is forming some sort of Kagome structure. And what we have seen is that, or people already, it was known that you can, by the application of hydrostatic pressure or chemical pressure, you can sort of suppress down the long-range magnetic ordering, go to a quantum critical point. So, and we invested a good amount of time utilizing USR, and what we have seen interestingly is that you can really see that both chemical pressure and hydrostatic pressure can suppress down the ordering, but most interestingly is that at least down to 250 50 millikelvin, we didn't see any appearance of Fermi liquid state. Rather, we saw an extended quantum critical phase. Okay, so now the point is that this was the sort of phase diagram that I already told. So probably because of the presence of frustration, you have an extended quantum critical phase. Okay. So of course, because of the frustration, we have a extended or emergence of quantum critical phase. So to the best of our knowledge, such kind of quantum critical phase was nicely been described by theory considering triangular and square lattices, but probably not that much elaborately explored for Kagome. If you know some work on that, please let me know. And of course, we also saw interestingly that in the quantum critical phase at lower temperature, we also saw some sort of quantum spin liquid like correlation, dynamical correlation. Fine. So now you realize that the compound with which we have started or did this kind of experiments, that is a highly anisotropic material. So while we are applying hydrostatic pressure in anisotropic polycrystalline material, things gets complicated, right? You do not know whatever you are saying is truly correct or not. In order to avoid that, we also applied external magnetic field on the same compound with a single crystalline compound, and we saw that there is also a critical spin liquid like state driven by external magnetic field if you are applying the magnetic field along the Kagome plane. Okay. And so far so good. So now the point is that what are the other sort of states that are that can be explored? One is definitely quantum spin liquid at ambient conditions, right? So whatever I have shown, all are sort of got tuned by external field or some non-thermal tuning parameter. So of course one can figure it or look for some critical spin liquid state. Actually, one of my students is also going to talk about one of such example probably on the last day. And also last but not the least, proximate quantum spin liquid state, on which I am going to talk about now. So the name itself is suggesting that the state of the system is defined by the fact that it is close to a quantum spin liquid state, but not quite. Okay, so two different possibility probably can give rise to such states. Since we are talking about different type of phase diagram in the parameter space, so you can see that sort of maybe this particular compound, which has probably some sort of ordering temperature, is close proximity to a quantum critical point, as well as it is close proximity to a quantum spin liquid state. Okay, so that sort of situation can give rise to a proximate quantum spin liquid state. But it is not necessary at all that you have to have a quantum critical point. Such kind of situation can also arise that the system is just the long range ordering and the quantum spin liquid state is just adjacent with respect to each other. Okay, so now the point is that what are the sort of candidates that are already there showing proximate quantum spin liquid state? Indeed, there are several, but all are sort of insulators. So now the question is that, as I told, that whether we can find such kind of state in metals also. So now, since we already have a list of compounds showing such kind of proximate spin liquid state, we sort of know that what should be the ingredients or what should be the experimental signature of such state. Okay, so one is you have to find some material which has a low spin value to promote quantum fluctuation. Of course, you have to have frustration, and the most important point is that what people have seen is that all the proximate quantum spin liquid state has a coexistence of both static and dynamical quantum spin liquid like state. Okay, coexistence of both of them. And last 2 points indicating very low ordering temperature and the presence of some quantum fluctuation above the phase transition temperature is not mandatory, because those 2 points is only going to be valid if I consider the first possibility I showed you earlier. Okay, fine. So now this is our intention, and so we actually looked around several compounds and find out this holmium, indium, copper 4, where copper is non-magnetic and holmium is a non-Kamers ion, have a magnetism there. And the holmium moments are sort of forming a FCC lattice. Okay, and what was known is that the ordering temperature for or the phase transition temperature for this particular compound was 760 millikelvin. The Curie-Weiss theta was found out to be minus 11 Kelvin. However, the Curie-Weiss theta in the case of metal does not really give you the strength of the frustration, because you have at higher temperature you have Kondo and other stuff that is going on. Okay, but the point is that the ground state is sort of S equal to 1 ground state because of the crystal electric field. Okay, so now you can see that for this particular compound, all this out of these 5, the 3 sort of conditions are getting satisfied. Yet to be explored whether there is indeed a coexistence of static and dynamic correlations or not. So in order to verify that, we have employed muon spin relaxation or rotation technique, as a microscopic tool. Of course, for the respect of time, I'm not going to talk about the technical details, but quickly going to go to the outcome, what sort of information one can get. So now the point is that the basics of muosr is that the name itself is suggesting that you are dealing with muons. So if you implant the muons in some interstitial position of the crystal structure, so what happens is that the muons has a finite spin half, and if the system is at lower temperature and if the system is at below a ordering temperature, then definitely the muon is going to experience some local field. And if it is experiencing some local field, it is definitely going to precess. And in the muosr data, you would be expecting that you can see that this muon asymmetry as a function of time. You see that the lower, please look at the lower curve, it is sort of, there are some oscillations that are present. If you take the Fourier transform of it, you get the local field that the muons are experiencing at the muon site. Okay, so if there is no oscillation, there is no ordering, that you can say, and it can detect ordering or static ordering which is of the order of 1 Gauss. Okay, so it is very sort of good in that. But if you are thinking about what is happening in the paramagnetic state, there is of course no oscillation, but you can feed the data by some exponential function, extract out the relaxation rate, okay, muon relaxation rate. So if you have a long range magnetic ordering, you would, okay, before going to say that, let me tell you that this lambda is actually proportional to the imaginary part of the dynamical spin susceptibility. So which means that the temperature dependence of the lambda is going to give you information about the low energy electron excitations or low energy spin dynamics. Okay, so now if you have a long range magnetic ordering, you would be seeing some peak in 1 over T as a function of as a function of temperature of lambda. But if you are dealing with let's say if you have a quantum spin liquid, then instead of a peak, you would see that in the quantum spin liquid state, you have a temperature independent lambda, indicating you have persistent spin dynamics. Okay, so there are actually 3 protocols associated with muosr. This is the zero field one. Weak transverse field is also one protocol which gives you information about the temperature dependence of the non-magnetic volume fraction. As for example, if you have a ordering, let's say around 40 Kelvin, you can easily expect that in the paramagnetic state you have 100% of the spins which are non-magnetic, right? And in the order state you would be expecting there are 0 spins which are sort of non-magnetic, right? So another, but last but not the least, is the longitudinal field experiment. Quickly saying is that this experiment helps us to identify whether the correlation between the electrons are static or dynamic in nature. Okay, so if the correlations are static, by the application of weak field, you will completely decouple the relaxation channel. But if it is dynamic, it is rather tricky to decouple the relaxation channel. Okay, fine. So I am going to talk about now the results, weak transverse field results on the compound on which we are worked. So first, the weak transverse field result, as I told, that gives you information about the non-magnetic volume fraction. So you can see below the phase transition temperature Tn, it does not show 0, but rather, let's say, stuck at 0.6, indicating that 60% of the spins are still dynamic, whereas the rest 40% probably shows some sort of static type of correlation. So it indicates directly that you have some sort of magnetic phase separation. So if you look at the zero field spectra, you directly can see that there is no oscillations that are present down to 300 millikelvin, indicating that there is no long range magnetic ordering, again indicating that this is rather a complicated or unconventional type of ordering. And you can easily see from the asymmetry also, you need 2 exponential in order to deconvolute the asymmetry, and we use this kind of function. And one of the lambda or the relaxation rate was found to be fast, we denoted it by lambda f. One was slow, we denoted it by lambda s. So now let us see that what is the temperature evolution of these 2 relaxation rates. First, let us see what is lambda f doing as a function of temperature. You can see there is a enhancement of this lambda f far above Tn. Okay, so that directly give you the information that you have definitely some strong frustration, because in the case of frustration, you have short range correlations that starts developing far above the ordering temperature. Unlike for a unfrustrated system where you would be expecting the divergence of or the enhancement of the lambda with reducing temperature just above the phase transition temperature. Okay, so the next part is that you see a power law divergence with some exponent might indicate some quantum fluctuation, whether 5 minutes. Okay, sure. So might indicate some quantum fluctuation. However, we do not claim that it is definitely a signature of quantum fluctuation. Just keeping that in mind, we realize that the ordering is at very low temperature. There is a good chance that it might show some presence of quantum fluctuation. And the main important point is that lambda F completely sort of saturates below Tn, indicating the similar kind of quantum spin liquid like behavior. Okay, so and whereas the lambda S, the slow component of this lambda, sort of reduces below Tn, probably indicating some static phase. So this was further more verified or further verified by the longitudinal field experiment. Let me show you quickly that this is the sharp component. So this is the zero field data, the brown one. You can see by the application of 25 Gauss, the long component completely gets saturated. Okay, so indicating that the long component is associated with static correlations, whereas the sharp component is never going to be decoupled even after a field of 8,000 Gauss. So this further tells you that you have a coexistence of both static and dynamic type of correlations. So that sort of summarizes the fact that this holmium indium copper 4 satisfies all the probable ingredients to show proximate quantum spin liquid behavior. And now the last thing that I just would like to point out is that what are the known theoretical results on FCC lattice, which sort of says that there are some quantum spin liquid state that may be possible. Okay, so now I should mention that one recent neutron scattering experiment shows that for this particular compound on which we worked, is if you consider the J1, which is the nearest neighbor interaction, and J2, which is the next nearest neighbor interaction, they have found out that the ratio of J2 by J1 is half. So we look for those theoretical results where they have considered this J1, J2 model in the case of FCC lattice. So one of such approach, I mean, it is just some few apart from, I mean, we are not going to show all the results, but these two results that I'm going to show. So people have done this kind of approach, like perturbative series expansion at zero temperature approach. They saw that around this J2 by J1 ratio of 0.5, there is a sort of boundary between two different type of antiparamagnetic states. So it is highly possible that around this regime there is a sort of degeneracy between these two sort of states. And even more recently, both of these two papers following this pseudo-fermion functional regeneration group approach, they indeed saw that there is a possibility that J2 by J1 at around 0.5 of having a spin liquid. Of course, they didn't consider our compound or some metallic compounds, they just considered some another frustrated insulating compounds, but at least we are sort of thinking that it seems to be quite in the right direction. But of course, as I told, that cultivating the spin liquid state around this zone boundary between two different antiferromagnetically ordered state is yet to be explored. So now, keeping all the points in mind, we constructed this kind of phase diagram. Is that you can see that this is one of the compound that I talked about, holmium indium copper 4. This is the proximate spin liquid state. We do not know whether there is a QCP or not, because we have not employed any other technique to really reduce down the ordering down to T equal to 0, but we at least expect that there is a quantum spin liquid state proximate to this particular compound. And we also actually studied this compound on the same family, but you are replaced, the indium is just replaced by cadmium, which doesn't show any sort of signature of frustration, and it shows complete long range magnetic ordering. And this is the type 3 type of antiferromagnetic ordering for holmium indium copper 4, and this is this holmium indium cadmium 4, it is a type 2 ordering. And again, we do not know whether there will be a QCP, but this is the sort of phase diagram that we sort of proposed. Our paper is on archive, and thanks for your kind attention.
Questions?
Yeah.
So maybe backside module here, that's the reason it's better to use. Yeah, so thank you, Mayuk, for this interesting talk. So regarding this holmium, this indium copper 4, is this a single crystal? No, it's
This is a polycrystalline.
It's a polycrystalline.
Yes, yes.
Okay, so actually what is actually provoked me that essentially if we can really tune the system, yeah, because you are targeting this metallic proximity to the quantum spin liquid state, so that means it's always good to tune the system in one direction.
Right.
So therefore, it's good to have a single crystal for this
Yeah.
system.
So as I told that the sample has been synthesized by our collaborators, and they have single crystals. So in principle, if we really think about some uniaxial pressure or something like that, that in principle can be done in the future. Yeah.
Quite interesting. I'd like you to comment on the competing time scales in the problem. A, you have the mu on lifetime itself, which is a microsecond, 10 to the minus A. Then you have the spin relaxation time, though you showed 2. One would expect that in a disordered, frustrated system, you may have a combination, you have a distribution of relaxation times. And then you also have the Larmor precession time in a local magnetic field. Would you like to comment how they compete and you see the transition from the oscillatory to the relaxation behavior?
Okay, so the range MUSR can sort of detect the spectrum, full spectrum, depends on the gyromagnetic ratio of the muons, along with the sort of radioactive decay of the muons. As you know, it is of the order of 2.2 microsecond. So which means that around that value, whatever the excitations that are happening, you would be able to know. And along with the fact that this gyromagnetic ratio is 135 megahertz per Tesla. So that's why whatever the relaxation rate we showed, it is of the order of microsecond. That is why. So we are in that range. So it can of course happen, since we are dealing with some like systems where these are dynamically fluctuating systems. It can of course happen that in some system it is dynamic in the Mueller time scale, but not dynamic in neutron or NMR or other time scales.
Okay, just another question, quickly. You're actually talking about a quantum spin glass-like phenomenon. And do you have any role of the Edwards-Anderson order parameter in this case?
No, so quantum spin glass, I would not say in the sense that, so the compound that we are looking into, or the other compounds that in which people have found this proximate quantum spin liquid in insulators, all are structurally perfect. Of course, that may also give rise to a spin glass type of thing, but for this compound, people have performed different experiments, completely sort of discarded the fact that there is no spin glass as such. But there is a phase coexistence. The phase coexistence is only happening because of the fact that it is close proximity to a quantum spin liquid, not due to the disorder induced phase separation. Yeah, that is our feeling. Yes.
Thank you.
I have just one question. You showed this lambda below Tn is sort of constant.
Yeah.
What will happen if suppose that had decayed down, softened down?
Yeah, so that is a nice question, and related to the question that Professor asked is that, for if you are dealing with a let's say spin liquid system, usually if you look at, let's say, NMR results, so which probes even more low energy excitations, there you would expect that the lambda is decreasing following some power law exponent. But for the case of MUSR, since it cannot sort of detect that low energy with respect to MUSR, so what happens in the spin liquid regime is that it is completely blind to whatever is happening. But since it is temperature independent, it is indicating that there is a persistent spin dynamics. So as it is, and that is the same reason, because of the fact that if you really would like to know a highly sort of, let's say, spin singlet state in MUSR, it is really difficult to figure it out from zero field MUSR. Yeah.
Two more questions and then we.
Yeah. Nice talk, sir. I just want to ask, like in zero field MUSR measurement, you have showed that lambda relaxation.
Right.
So in this type of system, there may be spin relaxation as well, or spin lattice relaxation.
So why?
And,
Yeah. Okay.
In
Please.
your slide, you have shown said that enhancement of lambda is because of the frustration.
Right.
So how can we differentiate that it is because of spin lattice relaxation, spin relaxation, or it is from frustration?
Okay, thank you for the question. So, okay, there are several things I have to discuss. Maybe after that we can discuss. The point is that whenever you are doing or performing zero field MUSR, then the lambda that you are seeing, that is the longitudinal relaxation rate, indicating only spin lattice relaxation. Whenever you are performing some transverse field MUSR experiment, or if you are in the order state, let's say, of course we didn't have any ordering, if you are in the order state, then only you can get an idea about the spin relaxation rate, okay, which is the transverse component of the relaxation rate. So here, whenever we are talking about zero field MUSR, we are only talking about lambda L, which is spin lattice relaxation. Okay, so that's why the enhancement of the lambda is only from spin lattice, and usually for a normal unfrustrated system, the lambda shows the enhancement with reducing temperature just above the ordering. But here we saw that it is almost like 10 times more than the ordering, it starts enhancing.
Okay, good.
Yeah.
Last question.
Okay.
Nice talk.
Thank you.
You said that you had in the FCC lattice.
Mhm.
In the FCC lattice, you had two antiferromagnetic orderings which were meeting around point.
Right,
somewhere.
right.
And at that point, you had like quantum spin. You expect quantum spin liquid state.
Yeah, I mean,
Is
so
it also for an insulating or specific to the?
So, in the case of FCC lattice, maybe all the other theoreticians may sort of give me more information about it. Whatever I have seen, that in the case of, I mean, the results that I have shown, the theoretical results that are only on insulating. They didn't consider the quantum lattice model or other model related to metal. So, but in this particular case, what I can say is that in the case of FCC lattice, that regime where there is a phase boundary between two different states, that is very tricky to deal because there are multiple degenerate states that are around. So we could only find those two, I mean, like showing. Okay, anyway, so that's the point. We are definitely expecting, there is only two papers that hint that there is a probability that there might be a spin liquid, but no detailed study is to the best of my knowledge.
Thank you.
Yeah,
Okay. Thank you.
thank you.
You're hiding.